Hi, this is a brief presentation, well, maybe not so brief, on logistic regression. So what is logistic regression? Basically, it's a form of regression analysis like that you've been doing so far with linear regression, but the outcome variable is typically binary or multinomial in some cases. Logistic regression is a special case of the general linear model, which we've been going through when we talk about one-way ANOVA, factorial ANOVA, ANCOVA, repeated measures ANOVA. It's basically another special case of this general linear model framework. In a nutshell, it's a statistical model used to look at dichotomous or multinomial outcomes using predictor variables. These predictor variables can be continuous or categorical in nature. Used when the research method is focused on whether or not an event has occurred. That's the most typical approach. You see it a lot in the medical journals when they talk about whether someone has a disease or doesn't have a disease. So whether you can classify them as, having experienced the event. That's what they sometimes talk in terms of the event, or not have experienced the event. So what is the logistic component? So instead of modeling the outcome directly of y, or whatever you want to call it, directly, the method models the log odds using a logistic function. So you're not modeling the outcome directly, but the odds of the function occurring. So this is the logistic regression model in the most basic form as compared to the linear regression model, which you're much more familiar with at this point. Let's see if we can dissect it a little bit. So we have in the red circles on the left-hand side, we have the dichotomous outcome in this case. So we can say whether or not someone drops out of high school or doesn't drop out of high school, which would probably be the most relevant example in education as a function of predictor variables. So their family background, their previous achievement level, their sense of school belongingness, etc., etc. So ln in this case is the log odds, or the natural log of the outcome. So you see you have the probability of y over the 1 minus the probability of y. So the probability of y being, they do retain and graduate versus not graduating. So 1 versus 0 in this case. Now, a question I often get asked is, in what order do I put predictor variables? A good rule of thumb is, one, to look at previous research, but second is to think of in terms of less malleable to more malleable. What I mean by is changeable. What are things that you can actually change as a future principal or higher education professional? So, SES, you really can't change your kids' SES. You can't change their gender. You can't change their family background. So usually those are the first variables that you control out for, because you really can't do much about those. And then you enter later into your model the variables which you can influence, like the sense of school belongingness. Those are more malleable variables, and that's what you have to be concerned with as a principal. Well, what can I actually influence as a principal or higher education professional, and increasing retention at even the post-secondary education level? Okay. Where was I? Okay, and then you have, encircled in blue, you have the intercept, the b sub or beta sub o, plus the beta sub 1, the beta sub 2, the beta sub k, depending on how many predictors you have. These are the model coefficients. These are what you're actually estimating in your model. So what is the influence of these variables? So logistic regression uses odds ratios, and some of you, odds ratios will be very easy to understand if you have a gambler in your family. I have an uncle who bets on horses, so I heard odds growing up all the time. 3-to-1 odds, 2-to-1 odds. Anyway, so basically we're not modeling the outcome directly, but we're modeling the odds of it happening. Estimates of effect are quantified by actually the odds ratios in the end. So for each predictor, you will have an odds ratio, which we'll get to. So what are the odds? Odds of an event are the probability of the event occurring over 1 minus the probability of the event. And the event in our example, I guess, would be the event meaning someone actually graduating versus dropping out. So 1 versus 0 in this case. And the probability of an event is the odds of an event over 1 plus the odds of event. So they have a clear relationship there. Estimating a logistic regression model. Steps we need to take to do this, at least conceptually, is observe the data on outcome Y, so whether or not they graduated high school, and characteristics, meaning our x1, x2, x2 are predictor variables. And we estimate the model coefficients usually using maximum likelihood. And then we perform the inference. We calculate confidence intervals, odds ratios, etc. on a predictor level. So looking and examining each individual predictor. So why not just use linear regression for dichotomous outcomes? Well, if we model Y directly and Y is dichotomous, this violates assumptions of linear regression. Well, homoscedasticity for one, and one of the more intuitive reasons is that we will end up with predicted Y's other than 1 or 0. So if we were to request the predicted Y values, in this case, in just performing a linear regression, it would predict Y values other than 1 and 0. But 1 and 0 are the only Y values you can have if your variable is whether or not someone's graduated or not, because that's the way the data is structured. So the key thing here to remember is that you should always respect how the data are structured. You know, if the data are structured such that they're categorical, you should let them be categorical. And if they're continuous, you should let them be continuous. Do not dichotomize or categorize continuous variables. You should respect the data in its structure, in its form. So you respect the data, respect the structure of the data. Let the data be the data. Anyway, that's the soapbox. So, what are the assumptions in logistic regression? One, that the Y values are from the Bernoulli or binomial distribution, that they're independent, and that the log odds or logit is a linear function of the covariates. This shouldn't be that scary for you in the terms of the Y are independent. You're comfortable with that in terms of that the assumption of parametric tests in general is that the observations are independent, or else you can't do parametric statistics. And then a linear function of the covariates, that makes sense, because in linear regression you're assuming a linear function, except now the outcome variable is looked at in terms of log odds instead of just as the continuous variable in and of itself. So linear regression is part of the family of regression models and uses the general linear model framework. Here's a little chart to organize your thinking. If your outcome is continuous, and the GLM model you would use would be linear regression. Versus it's logistic, you would use a dichotomous. I mean, if your outcome is dichotomous, you would use logistic regression. Or if it's counts, you would use a Poisson regression. We could go on and on here. I just mentioned 3 in this case. And if it's multinomial, you can have a multinomial logistic regression. So this is not an all-inclusive table, but it should help you organize your thinking in terms of thinking, well, what is the structure of my outcome variable? Is my outcome variable continuous? No. Okay. What does it look like? It's dichotomous. Okay. I'm predicting a dichotomous variable. What analysis should I use? Oh, I should use logistic regression. So you should always be thinking in terms of how are my data structured. Hypothesis testing. We do 2 types of hypothesis testing in logistic regression, likelihood ratio test and the wall test. Now the wall test is omnipresent. It's everywhere. Everybody and their dog likes it, but it's not that great. But we don't mean to scald the wall, but it has some issues. Anyway, we'll get to that. Likelihood ratio test. The idea is to compare the log likelihood of 2 models to test. So you have 2 models. One is the full model with the predictor included, which is the conditional model, or I don't know if that confuses you guys, and then the reduced model without the predictor. Usually you test the unconditional model, which is the reduced model without the predictor, and then you test the full model, and you see if there's a difference between these two models. So you would take the full model minus the reduced model and look at the difference between them. And then that difference you compare to a chi-square chart, and you look at the degrees of freedom as the number of extra parameters in the model, in the full model. So basically it's a comparative model fit. So compared to having no predictors in the model, what is the fit? Versus compared to having your full model with predictors included, what is the fit? And some people will do this incrementally. They'll put in one predictor at a time and say, well, does this predictor substantially improve the model? And does this predictor substantially improve the model? Sometimes people do it in blocks. That's kind of a conceptual thing in some cases, because if your review of the literature has already established, yeah, this, SES predicts academic achievement outcomes, nobody's going to be impressed if you then say, oh, I'm going to incrementally introduce SES and see how it predicts academic outcomes. Nobody's going to, be clapping for you there. They'll be like, yeah, and? So it kind of depends what your literature says, because how much you do that, how much you incrementally enter variables into the model. So, but basically it's a measure of comparative fit. Then we have the wall test. The idea is it makes a z. It's equivalent to a z value in terms of it's the whatever the predictor is divided by the standard error of the predictor, and you basically set it at the critical value for z at 0.05, which is 1.96, two-sided of course, and you compare that value, and if you exceed that value in your wall test then of 1.96, then your predictor is considered significant. So you see there's two ways of doing this. You can do the likelihood ratio test or the wall statistic test, where you can either enter it incrementally using the likelihood ratio test or the wall statistic test. So it's similar to a t-statistic in regression, very similar. Test the null hypothesis that beta equals 0, and it is biased when beta is large, which is kind of similar to a t-statistic in regression. A lot of people prefer the likelihood ratio tests. I do personally. I think it's a much more detailed way of looking at things, a much more elegant way of looking at things, but a lot of people love the walled. As the sample size gets larger and larger, the wall test will likely approximate the likelihood ratio test, so that's the good news. So you can skull the walled as much as you want, but when you approximate the walled with the likelihood ratio, then it really doesn't matter which one you pick then. But I would say the likelihood ratio test is preferred, but the walled is definitely more common. Okay. Where are we? Okay, so predictive ability of the logistic regression. To measure fit, some people like to use the generalized R-square statistics, but they're quite controversial. I report them, but I don't put much stock in them. I'm a much more of a likelihood ratio test statistic kind of gal. But if you want to report them, go ahead and report them. I wouldn't wave your flag about them. I wouldn't say, oh, my Nagel-Kirk's R was blah, 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 or my Cox and Snell R, because a lot of people, they're controversial. And then you can also use logistic regression results to plot sensitivity versus 1 minus specificity in ROC curve plots. This is actually the number one way that I use logistic regression results, is looking at sensitivity versus specificity of measures. I'm right now looking at the social communication questionnaire and looking at ROC curves for that. But that's the way I use it. So, assessing the predictors, the odds ratio or exponent B indicates the odds and resulting from a unit in change in the predictor. So basically, an odds ratio greater than 1 is good. It's better because basically an odds ratio of 1 indicates that you could flip a coin. And it's like a 50-50 shot. If it's 1 to 1, then it's like, well, it could go either way, But an odds ratio of 1 is predictor increases, the probability of the outcome occurring increases too for every 1 unit change in the predictor. Odds ratio of less than 1 means that as the predictor increases, the probability of the outcome decreases. The probability of the outcome occurring decreases. So it's pretty easy to understand. We should mention that there's different methods of regression, and that goes for logistic regression as well as in addition to linear regression. You have forced tree where all variables are entered simultaneously. You have hierarchical logistic regression where variables are entered into blocks. This is the method I use most. I consider it what you should be doing. So you blocks should be based on past research. So you put certain variables into blocks saying, well, these variables are related to one another and they should be entered in together. And I consider this the best method of doing it. Stepwise, variables entered on the basis of statistical criteria, so relative contribution to predicting outcome. This is really for exploratory analysis, and it's kind of data fishing. You're just trying to say, well, what's significant? So I wouldn't do this unless you're really just exploring the data. I would recommend doing it a hierarchical logistic regression where you enter variables into blocks and then decide, well, this is, the way the literature has guided me to enter the variables. So, okay, I think that's it. That was a brief, I guess not so brief, presentation on logistic regression. Good luck on the homework.